So we classified everything from the top to the bottom. And we look at the procedure to solve the equation, but the how to do it. Again, how is not just the steps. It's about how you're going to look the system. We call it methodology. How do you divide and conquer the complexity? That's the question. So a compartment analysis, basically, you look at the state variable. In each time change, you look at a black box. That black box, we call it compartment. Why I call it a black box? Because except the input and the output and what you have inside originally, you don't have any other information. How they're going to mix it, how the molecules inside are going to resolve, we have no clue. We don't need to know. So compartment analysis basically treat each state variable as a compartment, as a box, a black box. And you trace the exchange of the content from the input and output from the interface. Well, here, so simple, you only got one box. Then you only got one variable. But in real world, you can have hundreds of boxes, like a chemical process. Well, thanks for the tool. Don't worry about the hundreds. If they are linear, you can do it. So what you are focusing is the first principle. What's the first principle? Anything change on the boundary. If nothing happened in the input and the output interface, nothing will change inside of this box. That's the first principle. So I write this first principle into equation. So the change rate of your state variable over a unit time equals the content right now and the content a unit time ago. That's just a definition. That's nothing but change. But this change right now and a moment ago in mathematics is a derivative, right? The change rate per unit time is defined as the derivative of the change in the continuous model. That's why we say it called continuous. And then how it changed? It changed from the input, subtract from the output. Well, that's obvious, but that's the starting point. How do you attack those problems? You look at the interface. If in this room, I close the door, we have 4 people. We always have 4 people. So if you want to trace the people change in this room, you look at the entrance of the door and the exit of the door to make it more easy to observe. There's one door, people can only enter. Another door, the people can only exit. And then, of course, the change of the people in the room equal the entering people subtract the exiting people, right? That's it. That's the principle you all agree. So our equation all built with this principle. That principle we call it compartment analysis. Look at my time. Well, I always start from the easiest example. I have a large tank hold 1,000 liters of brine solution, and that's unreal. The concentration is so much, 1 kilograms per liter. I should change into gallon if you want to be realistic. And then you read the story. You have a tank. That's how I usually do it. Okay, it holds 1,000 liters of brine. The brine has 1 kilograms per liter density. And what's happening? And a brine solution with low concentration is flowing in to the tank 4 liters per minute. Oh, there's a velocity here, flow in 4 liters per minute in. And the concentration is low density. The concentration in is 0.2 kilograms per liter. And then after you mix it, it flow out with the same speed. Flow out also this. So, okay, you got the picture. That's how I started to recall the fact. I write every fact as I read, so help me to memorize, right? You can use your pen. So that's the interest rate, and put it in equal that. That's the interest concentration, and inside originally have 1,000 kilograms of salt. Why? Because the density is 1 kilo per liter. And the flow out, only know the speed, the ratio of flow out is the same as in, then I can guarantee the volume does not change over time. The only thing I don't know is, hey, what is the concentration flow out? Well, I need to trace. What I said is I think I removed that important word. It's still uniform, have the uniform density. That's the important thing. But anyway, you got the idea. And the concentration, because I mixed it very well, should be equal to the total of salt inside of the tank divided by the volume of the tank. So in that case, because the volume does not change, my only state variable is this xt. Oh, that should be the starting point, actually. After you draw the graph, what is that xt? Is the amount of pure salt at the time t. Oh, our microscopic observation always start from this individual compartment. That's called the compartment variable. It's also called the state variable. That should be the starting point, is the question they're asking. Well, but still pretty messy. How can this be a differential equation? Well, believe or not, the differential equation is right here in the conceptual level. You do not know the quantity, but the qualitative, the change rate equal the input rate in terms of pure salt minus the output rate of the pure salt, right? Clear? Okay, I need to look at. So we built the graph, and the second step, we need to make the assumption of our conceptual model. When we read, oh, you said that the flow continues indefinitely, means give me the t goes from 0 to infinity. That's my time. And the brine inside is uniform concentration. Give me the concentrate out equal xt, the total salt, divided by the volume. That's from here. And third, that's where the equation comes from. All change of the pure salt result from the difference between the input and the output, the flow in minus flow out. Make sense? Okay. So you start to write everything that build your conceptual model. And the input rate is 4 liters per minute. Because you are considering the pure salt per unit time, then you need the volume speed times concentration. Can you see it cancels out this? You get the flow in 0.8 kilos of salt per minute. The flow out, I don't know. It equals the speed, the rate, times the concentration. That will be U divided by 220 kilo per minute. You cancel out the unit here. So, of course, you are considering the same unit, kilogram per minute. That's a quick checkpoint. Well, then what you get? Oh, flow in 0.8, flow out U divided by 250. That's what we get. And that describes the change per minute. And that's a derivative. In the beginning, you know you have thousands of kilograms of pure salt. And that we call it a mathematics model. You cannot be easier than this. But that gives you the baseline principle. We call it compartment analysis. Well, you can solve it. That's not the focus of this. But I can show you how to use Maple to solve it. I can show you how to use MATLAB, basically the same, to get this. But my focus in next hour is going to show you how do I know I got it right. So that's the third step. Build the mathematics model. You solved the mathematics model. What is the last step? Oh, what's the question? Oh, the question asks you, determine when, how long, start from the beginning. The concentration of the salt will be diluted to 0.6 kilo per liter. Oh, you need to answer that question. I have not answered yet. So when you get to that step, you need to make this equal how much? 0.6 times 1,000. That will need to be 600 here. That's the point. So in order to solve that, I need to let this UT equals 600. And then you can solve this by the logarithmic function. So you got 400 equal 800 e to the negative t, and 250, and you solve the t, which equals 152 minutes. Now you can answer the question as originally asked. Well, they say, okay, I'm done. Undergraduate, you can say you are done. But for your project, you are not even halfway. And how do you know you are right without the teacher to grade your paper? That's the learning you get from this next module.